Okay. I will start the class. I was waiting for some students. Okay, they can see the recordings, I guess.
They might join later.
All right.
Actually, I wanted to ask one question. The
Okay.
question I have posted in chat box like
Yeah,
this.
that s by s plus 3 the whole square, right? Yes.
Find the range of k for stability. How to do this?
Okay, 1 minute. I'll open the chat box. When did you post?
Just now, 2 minutes
Okay.
in this meeting chat.
Oh, meeting chat. Okay. This is the question from.
Quiz one. Like this is the transfer function in unity feedback system. How to find the range of k for stability?
Okay, let me open that question. Uh-huh. Oh, okay. Consider the unity feedback system with forward path transfer function. Finding the range of k to ensure stabilities. First, you need to find the closed loop transfer function, and then you can use the final value theorem to come to the answer. So, to get the answer.
Can you solve this once?
Yeah, I will solve one. You open in this tab and I will solve. Into s plus 3 to s plus 5 by. Okay, 5. G equals. This is the question. So first you need to find the closed loop transfer function for this question.
Yes, that
This
will
is
be
the
1 upon
open loop
1
transfer.
plus gs.
Yeah, the closed loop transfer function would be g of s by 1 plus g into h, where h is a unity feedback. So I'm considering 1 plus here. So this will be k into s plus 3 into s plus 5 divided by s minus 2 into s minus 4 plus k into s plus 3 into s plus 5. This would be the final answer. After this, uh, consider the characteristic equation because stability depends on poles. To find poles, we need characteristic equation. Whatever I'm writing is visible to you, right?
Yes, ma'am.
So the characteristic equation here is the lower part, the denominator part. Is s minus 2, s minus 4 plus k into s plus 3 into s plus 5 equal to 0. This will give you s square minus 6s plus 8 plus k into s square plus 8s plus 15 equal to 0. S square minus 6s plus 8 plus k s square plus 8 8ks plus 15k equal to 0. So collecting all the s square, this will give 1 plus k s square plus 8k minus 6 into s plus 8 plus 15k. This is the constant term. So the criteria is to uh, for the system to be stable, all coefficients of characteristic equation should be positive. So the condition here is 1 plus k should be 0, greater than 0. 8k minus 6 should be greater than 0. 8 plus 15k should be greater than 0. It should satisfy all these three conditions. According to the first condition, 1 plus k greater than 0, this will give you k should be greater than minus 1. This is the first condition. Second will give you 8k minus 6 greater than 0. This will give you k should be greater than 6 by 8. Second. Third is 8 plus 15k greater than 0. So this will give you k should be greater than minus 8 by 15. Is it right?
So,
Right.
and
Now,
why coefficient should be positive?
so, for example, if you take this transfer function, 4 equal to 0. When you find this roots or characteristic roots of this equation, it will give you s plus something and s plus something. Oh, so s plus a, s plus b. So when you find s is equal to minus a, s is equal to minus b. So this will let your poles in the left half of the s plane. Whenever the poles are in left half of the s plane, then only your system is stable. That's why. If you
Yes,
have
please.
something like minus or here minus, then you sometimes you will get s plus a, s minus b, or s minus a, s plus b. So this will make keep one poles, at least one poles on the right half of the s plane. So your system will be unstable. That's why. For a second order system, all your coefficient should be greater than 0, so that you will get a positive roots, negative roots that lies, those roots will lie in the left half of the plane, that in turn turn your system to be stable. So these are all the conditions you find. So the k should be minimum greater than minus 1, greater than 6 by 8, greater than minus 8 by 15. Out of all this criteria, look for the option that fits better in the given option. For example, A is k is greater than 6 by 8. So this satisfies. A could be one possible answer. B is k should be less than minus 1. I think I made some mistake.
Oh, yes, ma'am. I wanted to ask this one. Like, won't it be A because I am marked A only?
S plus 2 s square. This should be k should be greater than minus 1. Right only. Okay, right, correct. Okay. The second option is k should be greater than lesser than minus 1, and k should be greater than 3 by 4. 3 by 4 will be equivalent to 0.75, right? Out of this option, you can see 6 by 8 also will be equal to 0.75, I think.
Yes, ma'am. It's 3 by 4.
3 by 4.
Yes,
So
ma'am.
this satisfies this contradicts this option but satisfies this option. So we are keeping B aside for now. So A is not good, B is not good. We are looking for C then. C option tells k should be less than minus 1. This is also not correct because this contradicts this. So we are ruling out C. D option is minus 1 less than k minus less than 3 by 4. There is no upper bound for this equation right now we found, because according to this equation k should be greater than 0.75, but here the upper bound is 3 by 4, so the D option will also be wrong. So out of this, we couldn't find any of the options now so far, right? So there is one trick, so that if you see closer this, minus 8 by 15. This 8 by 15, if you calculate, I will tell in denominator. 8 divided by 15 would be nearly 0.53 something, right? It should be, so k should be greater than at least minus 0.5, and 6 by 8 is 0.75. So grade should be greater than 0.75. So k should be greater than minus 1, right? So the out
Yes.
of all, the better option that suits this upper bound and the lower bound is B option, because it lies between minus 1 and 3 by 4. So this is suitable. This is a suitable option. So the correct option is B for here.
So k should be less than -1 or greater than 3 by
Yeah,
4.
or greater than 3 by 4. Minimum bound for k is, or maximum bound for k is minus 1 here, and it should be minimum greater than 3 by 4.
Okay, so less than -1 means that it is satisfying minus 0.5 criteria also.
Yeah, right.
Okay.
That's why we are choosing B option here.
Isn't this question a bit tricky? Like it's not direct.
Yeah, little. Yeah. Right.
Yes.
That's why it carries higher marks.
Yes.
Right. Since we have quiz 2 on August 3, we will try to solve as much as problems based on week 5 today, so that we can start week 6 and 7 next week, because those are little hard topics. You need so much time to spend on those weeks so that you will perform proper in the exam. So we are winding up today the problems based on week 5. So if you have any doubts in week 5, you can ask now. We can also solve some problems based on PPAD controllers.
Yes, ma'am.
Right. I will start with an example problem. Steamy can solve, I guess. Okay. Right. We'll start with some simple problem first, then I will solve a little complex factor. Okay. First question, a control system with PD controller is shown. I am drawing the picture of it. I am giving velocity error constant kV equal to 1000, and damping ratio tau is equal to 0.5. And I'm asking, the question lies on what is the values of Kp and Kd. The controller gain I'm asking. Since we are using PD controller, I want to know what is the P's gain and D's gain. So the control system will look like this. This is the controller we are using. Kp plus Kd into S. If it is Ka, it will be Kp plus Ki by S. So this is the transfer function of the plant, 100 by S into S plus 10. Y of S. I'm considering unity feedback, unity negative feedback. So this will be 1. Right now. So first, we should identify what are all the information that is given. They have given the planned transfer function, open loop transfer function, that is 100 by s into s plus 10. So from this, you can say this is a type 1 system, and they have given a controller GC of s. So that is the KP plus KD of s. These two variables we don't know. We are going to find these variables. And the known inputs are KV error constant they have given. Since it is given error constant, the inputs must be RAM signal. This is the indirect information we can get from that. And the one additional information they have given is damping ratio of the system. So for the second order system, they have given the damping ratio that is 0.5. From this, you can know the system is under damp, right? The GDA value less than 1, so the system is under damp. The options they have given, so I'm not going to give the options, we are going to straightly solve the problem. So from this, first, how can we connect this KV to KP and KD? Just think about it. So this KV will give you the velocity error constant. You know the transfer function. You know the formula for KV, that is KV equal to limit s tends to 0, s into g of s into h of s. Right? How this g of s would look like? For example, this g of s is with the controllers. So the feed forward gain will be considered all together. So FFG will be Kp plus Kd of s into this g of s, because all are in the feed forward gate. So the open loop transfer function now with the controller becomes g of s is equal to Kp plus Kd into s into 100 by s into s plus 10, right? So this will give you 100 Kp plus 100 Kd s divided by s into s plus 10. So this is your new open loop transfer function with the feed forward gain all together in the forward path, right? Now we are going to apply this, use this g of s in this formula kv. So kv, you know, kv equal to limit s tends to 0, s into 100 kp plus 100 kd into s divided by s into s plus 10. Right. Now you know something, some information about this is kVs they have given us 1000 here, right? Since there is a two unknown variable, you cannot find the answer in this one particular step, but we will try to find one equation so that we can find the another equation from the another known input. This will become 100 kp plus 100 kd. Yes, this s will get cancelled. So writing like this. Right, by s plus 10. Okay. So putting s is equal to 0 will give you 100 kp divided by 10. So kp equal to 100. Right? We found one variable. We are left with another one variable, that is kd. So using some other another information that is given as zeta, we can find the next equation. So how zeta and this information will be connected? It is using the characteristic equation, because when compared to the standard controller definition 2 zeta omega n s plus omega n square, so you have a zeta here. So if you write this closed loop transfer function in terms of this, you will get this denominator transfer function compared to this. So s into s plus 10 will be in the format of 2 into zeta 2 zeta omega n s plus omega n square. So this will be 2s s square plus 10s plus 0 equal to 0. This is your characteristic equation, where you know 2 zeta omega n will be 0, 2 zeta omega n will be, oh sorry, I forgot to use the closed loop transfer function. I have taken the open loop transfer function as it is. Right. The open loop transfer function is 100 kp plus 100 kd s divided by s into s plus 10. So if you find the closed loop transfer function, This will become 100 kp plus 100 kds divided by s, right? S into s plus 10 plus the whole numerator as it is. It's difficult to write. This will give you s square plus 10s plus 100 kds plus 100 kp. Kp you already know. You can use the kp here. This will give you 100 into, what is the kp? 100. So this will be 10,000 plus 100 kds by s square plus 10 plus 100 kd into s plus 10,000, right?
Yes, ma'am.
Right. So comparing the transfer function with the standard form, 10 plus 100 kd into s plus 10,000 equal to 0 to omega n square equal to 10,000. Omega n would be 100. 10 plus 2 zeta omega n equal to 10 plus 100 kd. 2 zeta, you know how much is zeta? 0.5, right? 0.5 into 100 equal to 10 plus 100 kd. So this will give you 100 of 100 equal to kd. This will be 100 kd equal to 90 kd equal to 90 by 100, 0.9, right? So we found both of this variable, kp equal to 100, kd equal to 0. Sorry, there is no minus, just point. So this is your answer. So it looks like a short problem, but it takes this much time to solve this. So according to the time, you will get marks. Okay. The point behind this is very easy. Like first, you should know what are all the information that is given in the question. Using the information, you should be able to relate the information to the question. So what is being asked and what is given. If you can bridge the gap between these two, you will be able to solve the questions. That's it. The first hint they have given is velocity error constant, and they ask Kp and Kd. The second hint they give is zeta. So if they haven't given this zeta, we would have not find the closed loop transfer function, right? So based on the question's information, you should be able to pick up the uh, type of solution you want to use. I hope this is clear. If you have any doubt, please ask.
Clear, ma'am. Clear.
We will solve little complex problem. Before that, we'll try to solve the question from the assignment if someone has doubt in that. In the assignment, it was given this control system was given, right? GC of S, and there is a disturbance. And there is a transfer function. Is into JS plus B of S. Right? So the question, first question was, oh, there is an information. J is equal to 10 and B equal to 5. This is the information they have given. So can we rewrite it simply using this information so that it will be easy for us to solve? D of S 1 by S into 10S plus 5. Okay, it's a unity negative feedback system. The first subdivision they have asked is they have given the controller if they consider it's a common controller, but according to the subdivision question, if the controller that is being considered is pi, it has p and I information, right? So it is a pi controller. Then what should be the value of ki to have an acceleration constant of 0.2? That is the question. So here the information given is Ka. Since it is an acceleration constant, it is Ka. So last time it was Kb. So we assume the input signal is ramp. So this time it is Ka. So the input signal is parabolic, unit parabolic signal. Right? If required, we will use this information also. For now, it is okay to know about it. Right. So now you should find a way to connect these two pictures, Ka with Kp plus Ki, and the information given as G of S. So how based on this last thing, we can do the same thing again. Now, if I replace this Gc of S equal to Kp plus Ki by S, and G of S is 1 by S into 10S plus 5. Now the updated open loop or loop transfer function would be multiplication of these two, because these two are in a cascade form. So Kp plus Ki by S into 1 by S into 10S plus 5, right? Good. So this will become Kps plus Ki by S 1 by S into 10S. Otherwise, I will write in this. 10S square plus 5S. Right. Now Kps plus Ki by S into 10S square plus 5S. That's it. I'm keeping this as it is. So this is the updated open loop transfer function for now. Good. Now, or I can write in this way so that I can see easily that the type of the system, right? So this will be S square into 10S plus 5. So this is the type 2 system, since we are going to use this acceleration error constant. So according to that equation, we know the acceleration error constant Ka equal to limit S tends to 0, S square G of S, right? So this is the equation. So let me put the updated G of S here. S square into Kps plus Ki by S square into 10S plus 5. Good. It seems to be easy when solving, when others are solving, you should solve by yourself so that you will know what are all the mistakes you are doing. Right? K equal to Ki by 5, where K is given as 0.2. It will be Ki by 5. This will become K will be 1. One information we have found. The next information is Kp. Okay. For now, they just asked in this question what is Ki. That question we solved. We are not going to bother about Kp for now. Right? If they ask to find the Kp also, they will give some other additional information like tau or omega n or some information. The second question is, where is that? I think I have closed that. I will open the question. 1 minute.
This acceleration constant is given because we are getting a square in GS function. So whichever constant we are given, like According to that only transfer function we will get. Is it so?
No. According to that, you should write this equation. Since it is a KA, here S square will come. If it is KV, the equation would be limit S tends to 0, S into G of S. If it is KP, they have given limit S tends to 0, 1 plus G of S. You should write in that form. But the G of S, you should not take this G of S as it is, because with the controller, the whole is this G of S, open loop transfer function. So you should multiply GC of S into G of S, then you take that as a G of S, updated G of S. That is the only thing you have to use here. Clear or any doubt?
Yes, ma'am. Okay.
Okay, right. This is on week 5, right? Week 5, graded assignment. The next question is, for the KI to be obtained in question 10, this is the next subdivision I am taking. For the KI obtained in previous question, select all ranges of KP. Oh, now they are asking KP. All ranges of KP which guarantee the closed loop system stable. Until now, we are using the information about the open loop system. Now they say you should find the KP value so that the closed loop system is stable. You can use MATLAB Python to solve roots for polynomial. We'll try by hand once. If it is not helpful, we'll go. Okay. Since they have mentioned the closed loop system, we are going to find the closed loop transfer function. So this is the updated G of S, right? KPS plus KI by S square into 10S plus 5. This is this updated G of S. So to find closed loop transfer function, KI by S square into 10S plus 5 plus KP of S plus KI. Good. Now writing the characteristic equation and equate it to 0. S square 10S plus 5 plus KPS plus KI equal to 0. So it'll give you 10S cube plus 5S square plus KPS plus KI equal to 0. Now this is positive, this is positive. KP should be greater than 0, KA should be greater than 0. These are all the two conditions we have found from this. Good. Now, I think that is the answer for it. Okay. What is the KI value we used? Okay. So for all KI greater than 0, the KP should also be greater than 0. This is the question. It was based on the question. This is the condition. But to find the right numeric answer, we are going to substitute KI equal to 1 here. Right? For K equal to 1, I already discussed this Routh-Hurwitz criterion for S greater than, S degree greater than where n greater than 2. For this, we will use this Routh-Hurwitz condition. We are going to see that in the next class, but I will just brief through it now. So instead of Ki, I am using the 1 here. So for this particular one, what are all the ranges of KP that is greater than 0? Numeric answer they are expecting, right? So that we are going to find. For this, we use the Routh-Hurwitz condition. Routh-Hurwitz condition can be written in terms of first row should be odd degrees, coefficient of odd degrees. So that is S power 3, S1. So S power 1, S1 is coefficient of S1 is 1. And the next row will be coefficients of even degrees. That is S square and S power 0. S square coefficient is 5, S power 0 coefficient is 1. Now, you are going to do multiply. For example, if this is you have written in terms of this, you are going to multiply this and subtract it from this. For example, you should multiply BC minus AD and put the C in the denominator. This is the operation you are going to perform until you left with only one number. So first is 5 into Kp minus 1 into 10 divided by 5. So this will give you 5 Kp minus 10 by 5. So this will be Kp minus 2 by 1, right? Kp minus 2. So I'm going to write this here. Kp minus 2. Good. Now, there is nothing to do operation here, right? So I am just putting 0 here. Now I have ABCD format. Again, I am going to multiply this with this and subtract this with this. Kp minus 2 into 1 minus 5 into 0. So this by Kp minus 2. This will give you 1. So I'm going to write 1 here. Since there isn't anything, I'm going to write 0 here. Now these two become 0. So I'm left with only one element. So I'm stopping here. This will exactly give you the coefficient. And after this, you cannot proceed to. Every time you will be left with 1 when it becomes s equal to 0. Okay. So now I have said that all coefficients of second order polynomials should be greater than 0 for the system to be stable, right? So according to that, or similarly, based on Routh-Hurwitz condition, this is the name of the method we have done now, Routh-Hurwitz method. So according to its condition, number of unstable poles will be equal to number of times the sign changes in the first column, right? This is the first column. So it is saying if the sign in that column changes, then the system is unstable. This is the first point it makes. First point is if there is any sign change in the first column, the system is unstable. This is the first point. Second point is how many times the sign changed that many poles are in right half of the S-plane. For example, if there is two sign change, there are two poles in right half of the S-plane. So if someone asks whether the system is stable or not, you just look for any sign change. If someone asks how many poles that are in the right half of the S-plane, since the system is stable, you should look for how many times the sign change. Now we are looking for the option to make the system stable. So stable in the sense zero sign change. There should not be any sign change. So you don't know this, right? Since there is a variable involved here, you are thinking that to make the system stable, that is what we are trying to find. To keep the system stable, the sign should not be changed. So the Kp minus 2 with the unknown factor should also be greater than 0 since everything is positive, positive, this is positive, positive. If this is positive, there will not be any sign change. That is what our condition should be. So according to this, Kp should be greater than 2. So for all the Kp's greater than 0, the system will work. Numerically, it should be greater than 2. So the minimum bound is K should be greater than 2 when Ki equal to 1. Right? Any questions so far? Do you have any doubt here?
Ma'am, it's clear. Am I audible to you?
Yeah, you are very less audible. Can you speak louder?
Yes, ma'am, it's clear.
Yeah, clear, right? Okay, okay. Right, good. Okay. The next question is, with the controller obtained in question 12, the closed loop system. Okay, good. Now we know the controller gain Ki equal to 1. Kp should be greater than 0. Whatever value you are taking, you can take. Now, the closed loop system transfer function, we found that Kp, we will put all the information here, okay? Where the closed loop transfer function should be. I'll just copy this. But now, substituting this value. For the system, the closed loop transfer function is stable or not? That is the question. So to answer that, this I'm substituting in the characteristic equation. Plus Kp should be greater than 0. For example, I'm taking 3. Plus K equal to 1. Whatever value you can take, considering Kp greater than 2. Okay. Okay, 3 yes. So now check 10s cube plus 5s square plus 3s plus 1 equal to 0. So all the coefficients are positive. So the system is stable. So whatever you put here greater than 2, that will be positive. It will stay positive forever. So always the system is stable. For the controller gain we found so far. Right? The option should be stable. Right. So this is the question from the graded assignment. In graded assignment 5, there is another question where people would have felt it little difficult. That is the 16th question. I can solve that. Rest of the things are little straightforward. The 16th question says, just decide to have a overshoot of the system to be less than 5%. So the peak overshoot they are giving MP percentage should be less than 5%. That is lesser than 0.05 should be. And settling time lesser than 1.5. TS less than 1.5. This is the condition there. To a unit step input. So that is 1 by S. Okay. The desired region for the poles of the closed loop transfer function is shown by this graph. There is 4 graph. So the desired region for the poles, where these poles can lie so that the system will exhibit the overshoot lesser than 5% and settling time lesser than 1.5%. So now they have given the poles location S is equal to minus 2.5 and the angle of the region they have given sine squared, right? That is, sorry, sine inverse of 0.69 and sine inverse of 0.45 they have given. What do you think the connection between the question and the graph?
Can you repeat the question?
Right. The question tells there are graphs. They have given 4 options of graph. I can draw that also so that you will get some idea. So they have given the region within that the poles lie. The region angle they have given that one option they have given is sine inverse of 0.69 and the pole region they have given is minus 2.6. Similarly, the next two options are minus 1.5, same, sine inverse of 0.69. C option is minus 1.5. This is little different, sine inverse of 0.45. D option is a combination of all the things we have seen so far. This is sine inverse of point, how much is that? 4.5. 4.5 and the poles lie in the minus 2.6. So the variation from this question would be poles can be minus 2.6 or minus 1.5. Within this is the first thing you have to find. The second thing is angle of convergence for the region. This can be either sine inverse of 0.69 or sine inverse of 0.45. All the four combination comprises of this information. So the given information is they have given the peak overshoot. MP percentage should be less than 5 and TS should be less than 1.5. So with this given information, if you are going to find what is the pole of the system or what is the angle and or which graph you should choose so that the system will give this desired specifications. So how you can connect this graph and this given information. We'll always start off with the known information. You know the equation for this, right? E power minus
Yes.
tau pi divided by root of 1 minus zeta square. This is the percentage into 100 if you put. It will become percentage. So all of this you need only one information. They have given 5% here. This will be 0.05 e power minus zeta pi divided by root of 1 minus zeta square. So this will give you ln of 0.05. If you move the e to this side, this will be zeta pi by root of 1 minus zeta square. Ln of 0.05, what it will give. Ln of, okay, ln of 0.05 into log. This will give you minus 2.99 something, around 3. You can approximate to 3. Right. I'm keeping it as minus 3. 1 minus zeta square is equal to minus zeta pi. This will become 9. 1 minus zeta square equal to minus zeta, sorry, zeta square pi square. And by finding all these things, you will get zeta, it should be greater than, because this is, sorry, I was giving the wrong thing. Should be less than, right? The simple is correct, I think. Zeta should be greater than some 0.69, right? So if you solve this, you will get this zeta value. Zeta should be somewhere should be greater than 0.69. So the next to known information they are given is settling time. That should be zeta omega n. You know, a zeta condition is greater than or equal to, so this should not be equal to. This will be tau s will be, since okay, equal to 4 by 0.69. Since this is the inequality condition, you have to consider, and omega n will be here. Right? Zeta is the only value you know, right? What else you know? You don't know anything else. Oh, sorry. We know this
Settling
tau
time
s.
in
Tau s we know. What is the tau s? 1.5. Good. That is also a less than condition. So we are going to replace this equality to less than 1 point. Tau s should be lesser than 1.5. So this should be right. Will be based on this condition. So this will give you omega n somewhere around. It will give 4. 1.5 into 0.64. Can you calculate? 0.69. 1.30, it gives 1.035 greater than 4 by omega n. So omega n should be 4 by 1.035 whole divided by 1.035. Maybe around 3.86, some value around 3.86 it will give. So you know that sine inverse, the poles can also be, the poles of the system can also be related to the second order system using this zeta omega n value. So this will give you the pole location for a second order system. Because when you write this, this is the characteristic equation. When you find the poles, this will give you based on this zeta omega n. So multiplying this zeta and omega n 0.8, 69 into 3.86 something, you will get zeta omega n should be greater than some 2.86 value considering this inequalities. So minus zeta omega n will be less than or equal to 2.6. So this is the one information we found that 2.6 is the pole location. So out of these two options, where it is. Out of these two options, the pole location should be minus 2.6. It should be lesser than minus 2.6. The another is we have to find this angle criterion. So for angle criterion, we have found already this. This is the angle criterion. So it should be greater than 0.69 and it should be lesser than minus 2.6. So based on this answer, you should choose option A, I think. Yeah, option A is the correct answer. Okay, so from week, I will just quickly conclude. From week 5, you will get questions based on PPI, PID gains. You have to find with informations related to time responses, time response analysis, parameters, like they may give zeta, MP, whatever we have seen so far, TS, TP. So you should be thorough with the formulas for each and every parameter, and you should be able to connect it with the open loop transfer function or closed loop transfer function, whatever way the question is. So you would expect this kind of problems where they will give the GFS, you will be asked to find KP, KD, or KI, or both. A combination of any of these two can be given using this parameters. So this is one type of question you would expect. The second type is KP, KI, KD based on stability. You can be, it might be asked. So based on the system or the controller difference, you will be asked to find whether the system is stable or unstable. So changing the controller gain, how it is changing the stability of the system. This is another dimensions of questions you would expect. So I'm concluding week 5 by today. If you have any doubt, we can shortly discuss on the next session. But my week 6, my Friday class objective is to start off with week 6. So be prepared for that class.
Yes, ma'am.
Um,
Ma'am,
yeah,
one thing, the
yeah,
question I asked from quiz one,
yeah,
like the option that we are marking k is less than -1 that I got, it is for -0.5. But
yeah.
won't it include even the other values that are less than -0.5?
Won't it include minus 0.5? Even minus 0.1 is greater than this, right? Sorry, longer than this, right? When considering the stability from this point of view. So we are taking the upper bound instead of taking the inner bound,
Yes.
right? If
Uh,
some value it is given coming around 0.3, then we will consider minus 0.5 at that moment.
okay, so less than -1 is the lower bound and
Yeah, yeah.
upper than 3 by 4
That's
is the
why we
upper.
are considering that.
Okay.
But I think we can wind off.
So why were we getting k is greater than -1?
K is greater than minus.
Like these three things that we calculated, greater than
Yeah.
-0.5, 0.75, and -1. Why are
Mm.
like greater than -1? Then what does that mean?
No, like these are all the three different options it should satisfy. But these all these options are not given in the solution, right? If it is a open question, you can choose either of this, like any of this equation. But since it is a MCQ question, you should connect the solution given in the question to the solution you are getting. So out of all the options, the B options lies near to this values. So we are picking up B because in if you see option A, it has only one bounds. Whatever it is greater than -1, it is accepted. That is not true, right? If it is less than something 0.03, then it won't come. So we should fix it properly. What are all within what range it should go.
So if we are saying k is greater than -1, then it is going to more negative value, -2, -3.
Yeah.
Okay, and greater than -0.5. Okay, yes, it is having two bounds.
Yeah, that's why we are trying to keep it between the range.
So this is the best range. This is not
Yeah.
the, but this is the best one.
Based on the questions option, this is the best range. It can be out of that also, but we are not caring about it right now because the options are not given broadly, right? That's why.
Okay, I got it. Thank you.
Okay. Thank you. You can leave if you want. If you have any questions, ask. Otherwise, you can leave. The recording will be available after 1 or 2 hours, so I'll update the link and I will put this notes in the G space.
Yes, ma'am. One more question I want to ask.
Yeah.
I can.
Yeah.
I mean, week 4 we studied that if we are having more zeros,
Mm-hmm.
the overshoot increases.
Mm-hmm.
From the mathematical equation I was getting, but intuitively I wanted to ask, like why increasing zero is getting more overshoot?
Why increasing zero is
By have
getting more?
by having more zeros increases overshoot.
Okay. For example, if you start with some s plus a, for example, s plus a into s plus b into s plus c. So if I add more zeros, you are telling like this
Yes, ma'am.
to a system. If I add more zeros, why it is increasing the overshoot? You are asking.
Yes.
Okay, it's just if you see the mathematical relation, sorry, mathematical formula between this overshoot will depend on the zeta value solely, no other parameters involved here. So when you take a closed loop transfer function here, so when you see a open loop transfer function, it is not going to affect any time. But if you when you take a closed loop transfer function of this s plus g, for example, this will become s plus b into s plus c plus k into s plus ca into s plus g. Now this zero in the open loop transfer function becomes a pole in the closed loop transfer function, right? So this contributes to stability. Now, so far, we will be seeing only the pole's nature for stability, but we will ignore the location of zero while just measuring the stability nature of a system. But when it is in an open loop zero, it will become poles in the closed loop transfer function. So when you write a characteristic equation, this will be in terms of z square zeta omega n plus omega n square, right? So when adding a zero, it will contribute to increase or decrease the zeta value based on the nature of zero you are adding, whether you are adding the zeros in left hand side or the right hand side. So this will increase indirectly affect the percentage overshoot. Clear?
Yes, ma'am. Ma'am, like one thing I was thinking, I
Uh-huh.
don't know if it is right or not. Like
Mm.
if in a system we are having some energy, if we add zero, it
Uh,
wants to go to zero. So
uh.
is it like it wants to overshoot and give up the energy fast so that it can go to zero more quickly? Like, is it right thing?
I couldn't interpret in this way. I can think about it and let you know.
It's when
Uh,
I got.
can you repeat the idea?
Ma'am, like if system is having some energy and we are giving
Okay.
a zero, it wants to go to zero. So it will shoot and try to give up the energy fast so that it can go more speedily to zero. If like
Okay.
if the overshoot is less, it is slowly going to zero by making a wave. If
Mm-hmm.
it will give up the energy instantly, by increasing the overshoot, it will more easily go to zero because energy is being dissipated, like in getting the overshoot.
Okay, I will think about it and let you know. I am seeing more that as a oscillation, this overshoot as a unstable behavior only, because when the system is in one state, adding this zero suddenly disturb or perturb the system. So it again go to overshoot and it takes some time to come back to that. But based on the nature of the zero, it will be decided how much time it takes to come from that peak overshoot to the normal steady state value. So I will think about your view also and let you know. Okay.
And this one I got. Thanks. Yes.
Right. Thanks. Okay. Can wind up, I think. If you don't have any questions.
Thank you.
Right. Thank you. Bye bye.